In the last section, we talked about the idea of a Riemann sum and how we could use this to start addressing the main question of Chapter 5, which is how do we find areas of complicated shaped regions. So we saw in the last section that we would use this idea of approximating rectangles to ballpark or estimate these difficult areas. And remember that we kind of came up with the following notation. We said that each rectangle would have specifically a width that we represented with the symbol delta x, and it would have a height which was ultimately determined by going to our function that we were trying to find the area under and plugging in a special point which we denoted with an x star, and then we had to pick a different special point for each individual rectangle. So as you can see here in the picture, we have x star number 1 for rectangle 1, x star number 2 for rectangle 2, and so on and so forth. So here I'll just note that as x star I, where I is just the rectangle that I'm currently referencing. So these were the bits of information that we had, and then we said that the net area, or the signed area of the region between the curve and the x-axis, which could be approximated by just adding up the areas of these rectangles. And we had kind of two ways that we thought about displaying this. We could take each individual height and multiply it to the width and get the area of a rectangle, and then add the area of the next one, and add the area of the next one, and keep going until I went through all of my rectangles. Or we were able to see that we could kind of more easily represent this with a summation. That is, it was telling me to just add up all of the different areas, starting with rectangle number 1 and going to rectangle number n. Remember again, xi star was just that special sample point that occurred somewhere in the interval, and remember that we always found delta x by just calculating the width of our total interval that we were working with and dividing by n how many rectangles we needed. So we talked again about all of this stuff in the last section, but what we want to take a look at here is how exactly would we begin to use more of this summation notation to represent our approximations. And so to do this, let's take a look here at example number 1. We're going to consider the area that occurs between the function x squared and the x-axis on the interval from 0 to 2. And we're going to approximate using right endpoints and a total of 4 rectangles. So for part A here, we just want to go ahead and carefully sketch out what this graph might actually look like. So since I'm going to try to be super careful here, I'm going to go ahead and use some of my tools here in this notes program to kind of help out. So I'm going to go ahead and sketch out my x and my y axis here. Okay. And if I was drawing the curve y equals x squared, of course I know that I would have this let me draw that a little better, but I'd have this parabola-like shape, right? Kind of moving out over to the side. And of course, I'd have it coming out into this second quadrant as well, but since I'm only working on the interval from 0, let's say, to 2, I'm not going to bother drawing that other half. So what would it look like then to go ahead and put my rectangles again inside of this particular region? Well, the first thing I'd have to probably do is figure out how much or how wide each of my rectangles is supposed to be. So I need to find my value of delta x. Now clearly my interval is 2 minus 0 units long, so it's 2 units long. And if I want to chop that up into 4 pieces, each rectangle has to be a half of a unit wide. So if the value of 1 is right here, then my value of a half and my value of 3 halves would be sitting at roughly these locations. So to draw my rectangles and to do a right endpoint estimate, I would again start with the bottom of my rectangle, go all the way up here on my right side, hit the function, and then come over. So this would be a rectangle, and I can do the same thing on each of my other sides for each of my other rectangles. Go up from the right, hit the function, and come on over. So again, this is the way that we thought about sketching these rectangles in the last section, and again we're doing the same thing here. But in part B, we're just going to be asked to express this approximation not by finding the area of each rectangle and adding them together, but by representing this approximation using the summation notation. So to do this, we're going to go ahead and note that to fill in that summation notation, we're going to need a couple different things. We're going to need to understand a formula that we're going to have for the width of our rectangles. we're going to need to understand a general formula that we would use to find the right endpoints for our rectangles, right? We need to know kind of what points we're plugging into our function in order to finally determine the heights of our rectangles. So let's go ahead and take a look at each one of these and then see how we can compile them all together to fill in this formula here. Okay, so the width again is super easy. In fact, we already calculated the width up here. So I'm just going to kind of re-summarize that down below. I have delta x. I know I should measure b minus a over my value of n. So I have the endpoint is 2, the start point is 0, and I'm going to chop that into 4 equal bits, so I get a value of 1/2. Now, to find the right endpoints of my rectangles, notice that's going to be the same thing as asking to find my x stars for each rectangle. Notice that my right endpoint for my first rectangle was 1/2. My right endpoint for my next rectangle was 1, then 3/2, and then 2. And so what I want to create here is a formula that depends on the value of I. That is, I want a formula over here that's going to have stuff with i's in it. And when I plug in 1 for I want this formula to compute the value of 1/2, the right endpoint for rectangle 1. If I plug in 2, that would mean that I'm looking at the second rectangle, and I want to calculate the second rectangle's right endpoint. Now, this can be a little bit complicated to kind of see how to do this, but ultimately, I can always think about doing things in the following way. If I ever want to get to the right endpoint, I can always think about if I started at the value of a, to get to the right endpoint of my first rectangle, I just have to move over 1 full width of a rectangle up here. If I want to get to the endpoint of the second rectangle, I would have to move over an additional width of a rectangle, 2 widths. To get to the third one, I would move over 3 widths, and to get to the fourth one, I would move over 4 widths. So I can think about doing something like this. I would say that my right endpoint can be found by starting at 0 and just adding widths of rectangles a certain number of times. Specifically, it seems that I want to always be able to do this I times. If I'm on rectangle 1, I only want 1 extra width. If I'm on rectangle 2, I need to make 2 widths, or 2 bounces over. If I'm on rectangle 3, I make 3 bounces over. So this could be a perfectly good formula. Now notice if I simplify this down, this is going to look like 0 plus 1/2 I, or just 1/2 times I. Now you can double check that this actually accomplishes the task that we set out at the beginning. If I plug in 4, this should tell me the right endpoint for the fourth rectangle. And notice if I plug in 4, I calculate the value of 2. And 2 is the right endpoint for my fourth rectangle. So I'm always thinking about starting at the leftmost edge and just adding over the appropriate number of widths, the appropriate number of delta x's. Okay, great. So now if I have that value, I can easily determine the height. The height of each rectangle I know is given by xi star. And so in this case, since my function is x squared, and my xi star value is 1/2 I would have this, 1/2 I squared. That's how tall each rectangle is. And so I can go ahead and kind of summarize all of this in the following way. I know that the total area under the curve is given by adding up the areas of all of my rectangles. Notice this is kind of the general form that we have for a Riemann sum. And if I was to write this out with summation notation and my specific values, notice I could say that I'm going to start adding up this approximation by starting at rectangle 1. I'm going to keep going until I get all the way to rectangle number 4, because that's how many rectangles I have. So n here is the value 4. I can see that f of xi star, we already calculated up here, is 1/2, not x, but 1/2 I, quantity squared, and the value of delta x is just the value 1/2. So this right here represents the summation notation that actually finds all the areas of all 4 rectangles and adds them all together. Now this might seem a little complicated, a little messy, a little intimidating. And if it does feel that way to you, I'd say you're right on track. Most people are fairly intimidated by this kind of new way of representing this actual sum. It was way easier in the last section where we just said, let's do a half and multiply by the height, and then a half and multiply by the height. But what we're going to see is that this particular representation here is crucial to be able to set up, because our goal in this section is to try to understand how might I be able to find the exact area under the curve.